to do the energy balance equation, and you consider this term mCp delta T as energy. So this is the general equation or conservation of energy equation for this example heating tank system. Rate of accumulation equal to rate of output minus rate of input minus rate of output plus rate of energy supplied by steam. Yeah. So accordingly, this is the equation. Fine. The individual terms we can substitute in the conservation of energy equation. And at the first look, we have this equation. Now, what do you think about reference temperature, T reference? Anyone? How much is T reference?
We can consider it to be 0 for us.
Say room temperature.
Yeah, is there any basis? Someone is saying 0, someone is saying room temperature. Sometimes we listen that 25 degrees Celsius. What is the basis of selecting this? Any idea? Anyone can tell what is the basis of considering T reference as 0 or 25?
The original energy equation involves differential equation. It is mCp dt. So we need to integrate it, and for integration we need upper limits and lower limits. So we take lower limit same for all the terms, which is T reference.
Okay. Any other answer? Anyone?
Like if we take T references 0, so like there can be one reason is the thermal agitation of matter at 0 Kelvin is like there is no thermal agitation, so we can take T references 0.
The third law of thermodynamics says that like all liquids freeze, like there is no motion at a 0 Kelvin, so we can consider that.
Okay. Any other reason? I mean, from engineering perspective. Okay, let me give the answer. This question quite confuses us. See, if you see this equation, Cp is there. Fine. If you recall the discussion on empirical model, we considered that enthalpy equal to integration of Cp dt. Can you recall this? Enthalpy, that is integration of Cp d capital T, and lower limit of that integration is T reference. Upper limit is the instantaneous temperature T or the system temperature. Can you recall this?
Yes, sir.
Yes. Now you say, what is this Cp? I mean, how we can calculate Cp, or what information available for Cp? Cp is basically a polynomial. Okay. So it is like A plus B capital T plus C capital T square, like this. Fine. Then we can integrate it, T reference to T, A plus B capital T plus C capital T square, suppose dt. Now this coefficients A, B and C, they are available with considering certain reference temperature. Do you know any data book which is very common in chemical engineering? Any data book, chemical engineering data book? Anyone know any book? Which, yeah,
Perry's
Perry's
handbook.
handbook.
good. Perry's handbook. Now there is another popular book available, The Properties of Gases and Liquids, written by, there are many authors. Lead author is Professor Prausnes. Okay. Now if you go to collect the data for ABC, suppose from Prausnes or Perry's handbook, you will see that they have reported this ABC data considering T reference equal to 25 degrees Celsius. Okay. Now, if you go to another book written by Henley and Cedar, same expression is there, A plus B capital T plus C capital T square, but coefficient values for ABC, they are reported at T reference equal to 0. Okay. So from which book you are taking the data and what value is considered there for T reference, you need to consider that T reference value. Fine. Now, finding these ABC values, they are not so difficult if you have the experimental data. So experimental data minus your predicted CP data, that is the error. Now, if you just reduce this error, minimize this error, then only you can find out ABC or the coefficient values for any equation. Anyway, let us avoid this because this is discussed under the course optimization. So this is the engineering, the answer from engineering perspective. You have to see what reference temperature, at what reference temperature the coefficient values are given. If they are given at 25 degrees Celsius temperature, you have to consider here 25. If they have considered with reference to, they are reported with reference to 0 degrees Celsius, in that case here you need to consider 0. Fine. Can you tell me what is Q? If we further want to extend this expression Q, what is the Q expression? Q is what? Anyone?
Q is the heat that is coming from the heater.
Yeah, you tell the mathematical expression. What is Q?
It can be like I square R into T.
No, steam is there.
No,
think
but it's coming from the heater.
No, you consider the heat which is going from steam to the process. Do not consider any upstream unit. Okay.
So
Yeah, you just consider here how much heat is going to this heating tank system.
the condensation.
Yeah. What is the mathematical expression?
Uh, m dot into latent heat of vaporization.
Correct. M into lambda. Fine. What's your roll number?
So 19CH 30024.
Good. Yeah, this is correct. So M into lambda. So what do you think? This steam is saturated steam, superheated steam? Which steam is usually used in industrial practice? Anyway, you try to find the answer. This is a valid question as a chemical engineer. Which steam is used or preferred in industrial practice? Fine, you find the answer of this.
Yes,
Which
sir.
steam is preferred in industrial practice? Saturated steam or superheated steam? Okay, so this is our expression. Let us consider T reference equal to 0. If we consider T reference equal to 0, then we have this final equation, you see, equation 2. Is this equation correct?
Sir, I didn't understand where Fi bracket Ti minus T this expression came from, because Fi into capital T, there is no expression like that in the previous statement. It's F into T, right? So
F into rho. Fi is volumetric flow rate into rho. Mass flow rate?
no, sir, I'm talking about the second term, F rho Cp T minus
This
T.
one.
No, sir,
I
in
think
the
you
previous
substitute
line.
this one. Substitute equation 1 here. Then see.
Okay, okay, sir. Yes.
Substitute equation 1 in the energy balance equation and then check whether we are getting equation 2 or not. Let me know if anyone got equation 2. Let me know if anyone got equation 2.
Sir, in first expression, we have to differentiate with H and T, right?
Yeah, H and T. These two are variables. Rest are all constant, no?
Yes, yes. So we can
Rho
substitute.
ACP. You take out rho ACP from this bracket because they are constant. Rho is constant, A is constant, CP is constant. Only H and T. Two variables are there. So you differentiate and substitute equation 1. So why are you taking so much time?
So on the left hand side, left hand side it should be dth dt instead of
D,
h
T.
dt.
Did you substitute equation 1?
Yes, I did. To
Then
replace f.
this will
So
be
on the
cancelled out. This term will be cancelled out. F into T. You do one
okay, so
thing,
let
you
me.
put T reference equal to 0 and divide both sides by rho CP. Do it.
Yes,
T
I did
reference
that.
0.
So, so
Then
here is what I
differentiate.
got. A h dt d capital T dt is equal to fi ti minus ft plus q rho cp, and then I replaced f with a dh dt, fi minus a dh dt. So like I'll try it again. Maybe I made a mistake.
This will be cancelled out, this term. You check.
Okay, sir. I'll try it again.
Yes, sir. It's cancelling.
Coming?
Yes, sir.
Yes. Substitute T reference equal to 0 and divide both sides by rho Cp. Then you differentiate and insert equation 1. Anyone else got?
Yes, sir.
Shubhada Rishi 10058. Subhada Rishi 10058. You are 10058?
Yes, sir. Yes, sir. I am.
Got the equation?
Yes, sir.
Can I proceed then, students? You tell me how else got this equation. Who else got this equation? Equation 2.
Yes, sir, I got it.
Got.
Yes, sir.
Okay.
Yes.
Yes, sir.
Yeah.
Yes.
It's not difficult, no? Anyway, let us proceed to the next one. Basically, we have two equations. You see, equation 1 and equation 2. We have two modeling equations for the heating tank system. Now we want to do the degrees of freedom analysis. Let us see how many variables are there. How many variables are there? Anyone can tell? What is the value for V? Unknown variables, number of unknown variables.
Sir, is
Sir,
it
6.
6, correct. Who told 6?
Sir, Varun.
Tell roll number quickly.
19CH 30036.
Yeah, 6. So what is the degrees of freedom then? Our V is
Sir,
6.
4.
4.
It will be
Correct.
4.
Yes. Oh, just before that you note down this one. Dynamic model and static model. Then we'll go to degrees of freedom. See, these are the two equations we got. These are called dynamic model. Okay. So what are the state variables here? 10046. Sanskar Singh. What are the state variables?
The state variables here are the height and
Height,
and the temperature
temperature,
and the feed rates.
conceptually wrong. Anyone else can give the answer? What are the state variables in this heating tank system? I mentioned state variables are present somewhere. Anyone? What are the state variables in this heating tank system?
HT.
H.
FI TI.
Who told HT?
Sir,
Yeah.
HN.
How you know? How you were saying?
Because the state variable are at accumulation
Correct.
expression which is at the left.
Correct. What's your roll number?
19CH30029.
State variables are present in the accumulation term. You forgot this. You see, these are the accumulation term. It's very easy to identify the state variable. This is accumulation term for total mole balance. This is accumulation term in energy balance. So here the variable present is height h. Here the variable present is temperature T. So height and temperature are the state variables. Do not do further mistake. This is a static variable, static model. What is the meaning of static model? In static model, there is no differential term. You see, that's why the left-hand terms are considered here 0. Static model means there is no variation of any variable in the model. There is no variation with reference to time of any variable in a model. That is static model. Fine. That's why these differential terms are 0 here. You see, I have considered here 0, here 0. Additionally, we have used one suffix s. S indicates steady state. Fine. That means these input variables are or output variables are also constant with reference to time. That's why this suffix s is only added with the variables, not with the constant. Very straightforward answer is all the variables remain constant with reference to time in static model. Let us go to then degrees of freedom analysis. What you told, this is a situation, you see. You told there are total 6 variables. That is why I have written V equal to 6. Parameters are identified as cross-sectional area A, density rho, and heat capacity Cp. There are 2 equations, model equations 1 and 2. So accordingly, capital E equal to 2. Based on this, we have degrees of freedom F equal to 6 minus 2 equal to 4. That means our number of unknown variables are greater than the number of available equations. Now, how to make it completely specified? Let me ask,
Sir,
100, just 1 minute, I am coming to you. 10013, Abharu Badri. Are you there? 10013. No answer. 10014.
Yes, sir.
Yeah. How to make F equal to 0? You answer at least. It may be wrong. Okay. Try to answer. How to make F equal to 0? Any clue, any hint can you give us?
So we can get more equations.
Yeah, how we can get more equations? We have discussed this in example 1, liquid tank system, in the last class.
So like,
Okay, 10018.
we can. Okay.
Yes, carry on, carry on.
So like we can have F is equal to Fs plus.
Capital F you were saying, no?
Yes, sir.
Yeah, F equal to capital S, capital Fs, then
Fs plus KCF in times of HSP minus H. And
good.
Yes, sir.
Good. Yeah. So one equation you have added. That's right.
Yes, sir.
Yeah. 10018. 10018. 10021. Mausam Sinha. 10021. 10006. Aditya. 10008. Akshay. Yeah. Now open to all.
Sir, we can
So
specify both number of disturbance variable, namely Fi and Ti.
Yes. Fi and Ti we can measure, no?
Yes, sir.
Yes, correct. What's your roll number?
19CH10002.
Yes. Yeah.
So
Thank you.
we can introduce one more equation.
Hmm.
With like F, we can introduce one more equation with energy like Q equal to
F is already correlated with H.
like similarly with heat Q equal
Okay.
to Qs plus K uh, Q into matlab TSP minus T.
Correct. What's your roll number?
So 149.
149. Yes, this is 149. Okay. I think you took you registered little late, no? 49. Yeah.
Yes.
Tell me your name.
Shalini.
Shalini. Okay, good. So I think we got the answer from all of you. You see, one of your friends, he told we can measure two disturbance variables. So I just try to remember you that there are two options. One is either we can specify more number of variables. Those are typically disturbance variables. And another option is to include or to increase the number of equations. These are the two options. We discussed this, we applied this concept to a liquid tank system. Now this is our second example and we are following the same, you see. We are specifying here two load variables. These are the only load variables for this example system, Fi and Ti. Specify means you need to simply measure. This is flow rate, so you can employ any flow meter like Venturi meter, orifice meter, rotameter, pitot tube, etc. for finding Fi as per the suitability. Temperature we can measure by employing any temperature sensor like thermocouple, RTD, like that. So naturally, if we specify, if we know two disturbance variables, our F further reduces from 4 to 2 here. Okay. Now for S2, we can consider this control variable manipulated variable pair for which we have these two controller design equations. Fine. And accordingly, our degrees of freedom reduces to 0. Any confusion, any doubt? If you have, you can ask me. So this heating tank system is completely specified. If you have any doubt, any
Sir, about this
confusion.
KCF and KCQ, how they are defined? Still they are
Yeah, I mentioned in the last class, no, these are tuning parameters. So controller tuning parameters, there are several methods. In fact, around 20% of your course content is attributed to finding this tuning parameter. Okay, 20% of your course is covering this I mean how to find out the tuning parameters. Okay, there are several methods we'll discuss one by one. Just for the time being, you remember these are constant values. And these constant values you need to specify in this equation. Like these are steady state values, no, I told. This is a steady state value of F. This is a steady state value of Q. Similarly, these are also constants, and these constants you need to determine by employing certain tuning methods, which we'll discuss in this course itself. Yeah, any other question? If not, we'll consider another example. And perhaps this is very important process for all of us as chemical engineers. I think we have discussed briefly this process. Okay. This is a distillation column. I don't know whether I told the importance of this distillation or not. Just let me, if I told, let me repeat. See, this distillation column shares 10% of the total industrial energy consumption in the United States. I repeat, this distillation columns, they share 10% of the total industrial energy consumption in the United States. I think you are understanding how important this process is, because this process is extensively used in the refinery industry. There are several other applications like in food industry, biochemical industry, petrochemical industry, but extensive use is there in the refinery. So let me give a little more about this. In the refinery industry, this feed is basically the crude oil. In the refinery industry, we basically fractionate the crude oil into several products like fuel oil, LPG, petrol, then kerosene, then diesel, then aviation turbine fuel. All these are obtained from the crude oil by the use of this distillation column. So you are understanding the importance of this column. Fine. At the top section, we get usually C1 and C2 components. C1 means methane, C2 means ethane, or their unsaturates. So at the top, we get C1, C2. Next to the top, we get C3, C4, that is, LPG, liquefied petroleum gas. But definitely there are certain other components also present, but mostly it is C3, C4, or LPG is dominated by C3 and C4. Then we get gasoline. Gasoline is the name which is used in United States, but in India it is called petrol. Okay. Then we get kerosene. Then we get light gas oil. In India we call it diesel. Heavy gas oil, like this way we get the products. Okay. So this is the use of distillation column in petroleum refinery. Now let us consider the basic structure of a petroleum column. In refinery, there are huge number of components, large number of components are present in the crude oil. Maybe 70 to 100 components are there. But to understand at this preliminary stage, we are considering only the two components present in the field. These two components are A and B. Fine, I repeat, we are currently discussing a simple distillation column to fractionate a feed mixture that consists of two components. One is A, another one is B. These are the name of the components. If we are considering as feed flow rate, and Z is the composition. Now I told previously that this feed may be 5 different types. I think you noted this. First one is it may be subcooled liquid. It may be saturated liquid. It may be liquid vapor mixture, like 20% liquid, 80% vapor, or 50% liquid, 50% vapor, like that. Fourth one is saturated vapor, and fifth one is superheated vapor. There are 5 different types of feed, and based on that the fractionation depends on. Now at the beginning, let us consider this feed as a saturated liquid, suppose. So if we introduce here, what will happen? It will go down. Okay, I am repeating the steps again to remind you the distillation operation. If we introduce the feed, it will move down because it is liquid, and it will directly come to this fill up. All the trays will be filled up, and the liquid will overflow over this weir. Then it will come to this reboiler. Although this reboiler is shown here very small, but reboiler is reasonably large unit. It's nothing but a heat exchanger. Now this liquid starts accumulating in the reboiler. The level increases. When it reaches a certain level, we start the heat input to the reboiler. This is the heat input. It's nothing but the steam. Okay, heat input means we are introducing steam. So if you consider heat exchanger, suppose this liquid are present in the tube side and steam in the cell side. It's somewhat like that. So if we introduce heat, what will happen? This liquid will evaporate. Not completely. Fraction of the liquid gets evaporated, and some portion of that accumulated liquid is withdrawn as B. Bottoms. Okay. Now this evaporated liquid is recycled back below the bottommost tray. Okay. Now initially the entire column is at atmospheric temperature, but this vapor has certain, higher temperature than the atmospheric temperature. This is the vapor stream. It has higher than the atmospheric temperature. So when it is moving up, it is basically heating the column. But at the same time, this vapor is getting condensed. Okay, because it is giving the heat to the column. No, column is at atmospheric temperature. So like this way, the vapor is moving up, condensing, moving up, condensing. Okay, the column temperature is also increasing. So finally, you will see that the vapor is coming out from the top. The vapor is coming out from the top, and this vapor we call overhead vapor or top vapor. This vapor we call as overhead vapor or top vapor. Then this vapor is getting condensed in a condenser, and in the condenser usually we use cooling water as a coolant. Cooling water we use as a coolant in the condenser. This is vapor, but this is totally liquid. This one is vapor. After condensation, that vapor gets liquefied here. Okay, and starts accumulating in this chamber. It's nothing but a cylindrical drum. Similar to reboiler, the liquid height gradually increases. And when the height reaches a certain level, we withdraw a portion of this accumulated liquid above the topmost tray. This liquid gets accumulated and the level gradually increases. When the level reaches our desired level, we start recycling a fraction of this liquid above the topmost tray, and another fraction is withdrawn from here. Okay, so by this way the distillation column operates. So this is what I told, the startup operation of the process. If we continue this startup operation, after a certain period of time, the distillation will reach steady state condition. I repeat what I explained. This is the startup operation of the distillation. If we continue this startup operation without withdrawing this distillate, then we will achieve steady state condition. Then at steady state condition onwards, we employ the controller, because at steady state what purity we are getting, that is the maximum achievable purity. At steady state what purity we are getting in the distillate and bottom, which are represented by XT and XB, those are the maximum achievable purity in this existing design. If you want to get more purity, you have to change the design. I mean, if you increase the number of trays, you will have better purity. Or if you increase, you need to increase this reflux rate, then also you can get more purity. Somehow understood, students, this distillation? Yeah, let me show the trays. The trays are like this, you see. This is the wall, tower wall. This is another tower, I mean another side of the wall. And these are the trays. The trays are like this. This is one tray. This is the weir. Okay. So this is the liquid height. So liquid basically comes to the next tray below this by overflowing over the weir. Okay. If we do not have weir, we cannot maintain this liquid height. So weir height basically is selected based on what liquid height we want to maintain here. Then it overflows and come to the next tray. Then it come to this side, like this way it moves on. And you see, these are the holes. These are the holes here. Through these holes, the vapor are going. The vapor stream is going through these holes. And here the liquid and vapor, they are coming to contact for mass transfer along with heat transfer. This is a typical tray I have shown. This is this portion only. Remember, only this portion. This is a tray. And these are the holes through which the vapor stream is passing, moving up. And this vapor here over the tray coming into contact with the liquid stream. And then mass transfer and heat transfer occurs. Let us explain about the how the mass transfer takes place. Suppose this liquid has both components A and B. The vapor has also both components A and B. You note down, I'm going to ask you the question. Liquid and vapor, they both include components A and B. Among these two components, A is the more volatile component. More volatile means it has a less boiling point. And B is the less volatile component. Okay. I repeat, the liquid and vapor streams, they are in contact over this tray. And both the streams contain components A and B. Suppose A has the boiling point temperature of 80 degrees Celsius and B has boiling point temperature of 100 degrees Celsius. You can note down these boiling points. A is suppose A has the boiling point of 80 degrees Celsius and component B has the boiling point of 100 degrees Celsius. Can you tell me which one is more volatile among A and B?
A.
A is
A.
more volatile. Yes, correct. And B is least volatile. Okay. Now you see, liquid and vapor, they are coming to contact. So usually more volatile component will transfer from liquid to vapor. Agree or not? I repeat, liquid and vapor, they are coming to contact. So what I'm saying that more volatile component will transfer from liquid to vapor phase. Agree?
Yes, sir.
This is the hot vapor, okay? So more volatile component A will transfer from liquid to vapor phase. You agree with this? So what happens? Which component will transfer from vapor to liquid?
B.
Yes. B. I think you understood this. More volatile component A is transferring from mostly liquid to vapor phase. Don't think 100% transferring is occurred here. And component B is transferring mostly from vapor to liquid. Because here in the liquid stream, the temperature you are rising. So A will evaporate first. But for this, the vapor stream temperature, suppose you are decreasing. So least volatile component will condense first. Most volatile component evaporates first in the liquid stream. That's why A transfer from liquid to vapor. Least volatile components condenses first in the vapor stream. That's why component B transfers from vapor to liquid. This is the way the mass and heat transfer occur over the distillation tray. Is this clear?
Yes, sir.
Okay. Something at least you have to know, otherwise you cannot understand, this model. Okay. Ideally, it should be, this subject should be, placed in the curriculum after mass transfer, but unfortunately it is not there. So still we have to discuss this, because at the end, if I do not discuss, you may feel that the process control is taught with only the liquid tank system. So that's why you try to understand as much as possible. And after mass transfer, if you go through this notes or course, you can understand. Yeah, if you do not have any question, we will stop here. We'll discuss tomorrow again this. Or if you have any question, you can ask me.
So for that question, I searched it, like it is telling saturated steam is preferred for heating applications rather than superheated.
What is the reason?
Because the superheated steam is more like air, like it has a poor heat transfer coefficient.
What heat transfer coefficient?
Poor heat transfer coefficient.
Poor heat transfer coefficient. Okay, better answer. Anyway,
like
you
more
think
superheated steam has more energy, and like so
then we should
can
prefer superheated steam, no? If
Yes,
it is
sir.
more energy.
Yes,
When superheated steam is
No,
used
no,
in the ducts, it loses energy to the ducts because it is at higher temperature. So there is a lot of heat loss happening.
That is true, but at the expense of getting more heat, no? We are getting superheated steam by spending more, but by consuming more amount of energy, you are saying. But superheated steam is giving us energy at higher temperature than saturated steam. Yeah, answers are coming, but not in clear-cut way. Okay, you consolidate all these answers and see which one is. I have mentioned one term in practice. So you have to think about the amount of energy as well as the cost. because whenever the issue is coming, to practical aspect, yeah, cost you cannot neglect. Cost is a major issue. So energy content as well as cost, these two issues you have to take into account in your answers. I think you will get. Okay.
Yes, sir.
Yeah. Thank you. Thank you, everyone.
Thank you, sir.
Thank you, sir.